Welcome everyone to today's quantum space lab seminar. Today we are very happy to have Chi-Ming Chang from Tsinghua University, and he's going to tell us about black hole operators in N equals 4. Over to you, Chi-Ming.
Hey, first, thank you for the invitation. I'm very happy to speak here. And my talk will be based on these 3 papers. And the first one is already 10 years old with my previous advisor, Chi-Ming. And the second one is from last year with my collaborator, Yin-Xuan Lin. And the third one is this year and with my student Tao Yixiao and another very good student, Feng Li, and also my collaborator, Yin-Xuan Lin. Okay. And so let me start by saying some general words about black holes. So first, black hole is a singular solution in GR. And usually people believe that the resolution of the singularity of black hole will require quantum mechanics. And a second important thing about black hole is that it obeys the first law of thermodynamics. And in particular, it has a large entropy proportional to the area of the event horizon. And because we have an entropy, then it's very naturally to seek for an interpretation statistically of this black hole entropy. And then that means the black hole should be an ensemble of E to the S microstates, and is a huge number of microstates. And this a lot of microstates cannot be explained classically due to the no-hair theorem in classical GR. And so the statistical interpretation of the black hole entropy will require quantum mechanics again. So we see that the resolution of singularity and the interpretation of entropy both requires the quantum nature of black hole. So black hole has been the most important testing ground for our understanding of quantum gravity. So because of these properties, and that Andy Strominger, to say these very famous words, I think you may already heard about this, that Strominger said that black hole is the harmonic oscillator of the 21st century. And we know that harmonic oscillator plays a very important role in the development of the classical mechanics and quantum mechanics and also quantum field theory. And so we will expect that black hole will play the same role in the development of quantum gravity in the 21st century. Okay. So the ADS-CFT correspondence is the by far best understood formulation of quantum gravity. So one of ambition we have is that we would like to build black hole as CFT operators in the non-perturbative complete setting of ADS-CFT. And then with this, we can study black holes rigorously. And the particular ADS-CFT setting that we will consider is the gravity side is the type 2b string theory on ADS 5 times S5, and the CFT side is N equals 4 super Young Mills. So it's basically the first example of ADS-CFT correspondence. And let me start by telling you something about black holes in type 2b string on ADS 5 times S5. So first, they are supersymmetric black holes. And because of supersymmetries, these black holes are the easiest ones to study. And we would pay a lot of attention of these black holes. And the particular property of these SUSY black holes is that it has 2 angular momenta that basically is the rotation, generate rotation on ADS5, and also 3 charges. They are the R charges that basically generate rotation on S5. And all these 2 angular momentum and 3 charges should be turned on microscopically for the black hole to have a large horizon. And these supersymmetric black holes preserve minimal supersymmetry. That means it preserves 2 supercharges. And N equals 4 super Young Mills has 32. That's being on the gravity side. The type 2b on ADS 5 times S5 has 32 supercharges, and that means these black holes are 116 BPS. So they correspond to 116 BPS states in n equals 4 super young mu. And in this talk, I will also discuss the near supersymmetric black holes, and in particular, focusing on the near horizon excitations of these near supersymmetric black holes, and they will correspond to the near supersymmetric states in n equals 4 super young mu's. And let me try to compare our approach with the more traditional approach to study the microstate of black holes. So the more traditional one is basically under the name of microstate counting, but our approach is more like microstate construction. And so let me compare them by listing some typical questions that people will ask in microstate counting, and then compare with the microstate construction, like the question that we are interested in. So in the microstate counting case, you will be interested in, for example, how many total states are there in the theory, and also does the number of states match with the semi-classical black hole entropy from the horizon area. And so we're also interested in that our microscopic models for these microstates, whether it will account for all the states in quantum gravity. But in the microstate construction that we are trying to do here, we are interested in more refined questions. For example, first, what are these states in CFT? So in particular, we would like to construct these states in CFT. And with these states, we can ask the next question: what bulk objects do these states correspond to? And also the third question is that whether we can study the dynamics of quantum gravity using these states. So in this talk, I will mainly try to focus on these the first two questions. I will not give a complete answer for these two questions, but I will give some results that we have for towards answering these two questions. Okay, so let me give a short summary of the results. So first, I will show you a complete list of operators that corresponds to multi-graviton states in the bulk. And the multi-gravitons, of course, are the states that are not that interesting. And because our main subject to study are the black holes. So the first result would just, and since we have a list of all the multi-gravitons, we can when we try to construct states, we can try to exclude those operators correspond to multi-gravitons, and then focusing on more interesting operators that has interpretation of black holes. And then the second result is that the first BPS operator in the SU2 n equals 4 super young mu's, which is not a multi-graviton operator. And but potentially you can interpret it as the smallest quantum black hole. And then I will also show you some results about the one loop anomalous dimension of millions of near-BPS operators. And then because we have the anomalous dimension for a lot of near-BPS operators, we can try to study the statistics of them. And then I will show you that we see some qualitative feature that is similar to what people have found on the gravity side from the near horizon excitation of near BPS black holes.
So Chi-Ming, these one loop anomalous dimensions would be big coupling?
Right. So yes, so it's one loop in a weak coupling. And of course, the bulk computation is at the strong coupling region. So of course, this is not an exact match. It's just we just see some qualitative feature that's similar to what people have found from the bulk. Okay. Any more questions? Okay, so we've done the introduction and summary part. So, and this is the outline of the talk. And first, I will tell you how we construct. I mean, I will first tell you what's our method of constructing these states, and we will focus on a sector that's called classically BPS sector, and in this sector we can turn our problem to some cohomological problem. That's called Q cohomology. And then I will also show you how do we compute the one loop anomalous dimension. And then I will show you more detail about our results on the graviton operators, black hole operators, and the near supersymmetric spectrum. And then discussion on outlook. So first, as I said, that we will focus on Engels-4 super Young Mills, and let me tell you some basics of Engels-4 super Young Mills. So the Engels-4 super Young Mills has the Engels-4 superconformal algebra, and it's this supergroup, and this supergroup has the bosonic subgroup as SO2,4 and SU4. And SO2,4 is the conformal group in 4 dimension, and SU4 is the asymmetry group of Engels-4 super Young Mills. And these are the bosonic part, and the fermionic part consists of 32 fermionic generators. They are the 16 supercharge Q and Q bar, and the 16 superconformal supercharge S and S bar. And this I index are the fundamental index of SU4 and run from 1 to 4. And this alpha and alpha dot indices are the spinor indices of the Lorentz group. And I write it as SU2 left times SU2 right. And they can take plus or minus. So out of the 16 supercharges, we pick one of them, and it doesn't really matter which one we pick, because they are all related by the bosonic symmetry, the Lorentz group, and our symmetry. So and we fix our convention to pick this particular one, and then in the radial quantization, it's conjugate to a superconformal supercharge S. And is this one, S minus 4. And with Q and Q bar, we can consider the anti-commutator of Q and Q bar. And by the superconformal algebra, this anti-commutator equals to some linear combination of charges. So D is the dilatation operator, and J left is the SU2 left angular momentum, and QI are the catan of SO6R or equivalent SU4R. And because the anti-commutator, because this combination equals to Q and Q daggers anti-commutator, so it should be non-zero. It should be non-negative. So we have the famous BPS bond. And for the operator that saturate this BPS bond are called the BPS operator. But instead of just focusing on BPS operator, we consider what we call the classically BPS operator. So basically, the thing we do here is, first, let's consider the, for example, let's look at the G Young Mills dependence of the right-hand side. And so since the J lab and the Q1, Q2, Q3, they are all quantized, they can only take integer or half integer value. They will not receive any G Young Mills correction. So they would not depend on G Young Mills. The only G Young Mill dependence would comes into the dilatation operator D. And at weak coupling, we can consider, we have this expansion. So D0 is the bare or classical dimension of the operator, and D2 is the one loop dimension, and D4 is the two loop anomalous dimension. And we can define the classically BPS sector to be the sector that includes the classically BPS operator and Rose operator satisfy this condition. Basically, we replace the D here by the D0. So these operators are BPS at 0 G Young Mills limit. And most of the classically BPS state or operators are lifted by loop effects. So the D2 and D4 and so on, they will give some positive contribution and then lift these classically BPS states. But some of them are not lifted, and they are the true BPS states. And the classically BPS sectors is, I mean, you may think that this only defined at 0 Yang-Mills coupling, but actually it can be well defined in perturbation theory. And that is because the higher loop anomalous dimension commutes with the classical dimension that just basically follows from the power counting in the perturbation theory. And so they cannot be operator mixing between the operator in the classically BPS sector and the operator outside the classically BPS sector. So this sector is well defined in perturbation theory. And we can further argue that it is well defined even at finite coupling. So to define a finite coupling, you need to have a way to distinguish which operators are in the classically BPS sector and which operators are not. And so at weak coupling, the classically non-BPS operator have the delta greater or equals to 1/2. That is because the classical dimension can also only take an integer or half integer value. So if you want to violate this equation, then it can only be violated by an integer value or half integer value. So we have we have this plot. So at G Yang-Mills equals 0, so these guys are classically BPS operators, and these are not. And then because by the level repulsion, we know that level crossing, so the crossing of this energy or dimension level can only occur at some codimension 2 loci in the conformal manifold. That's just from some very basic quantum mechanics. And now, because we also know that the conformal manifold is actually real 2-dimensional. So it's parameterized by the complex coupling tau. That's this linear combination of G Yang-Mills and the theta angle. And so the level crossing on this real 2-dimensional space can only occur at some discrete points. And we can actually find some path that avoid all these level crossing points. And suppose you want to define the classical dimension of some operator at finite G Yang-Mills, then we can just follow this path that avoid any level crossing point and to the G Yang-Mills equals 0 point. And then that gives us a way to distinguish which operators are in the classically BPS sector and which are not. Okay, let me pause a bit here. Are there any questions at this point?
So, Chi-Ming, then by that logic, you can distinguish the operators at every classical value of delta, right? All the green and the blue also you can distinguish.
Yes, right. So the thing I just said is that we can distinguish these and also the red, but true, you can also distinguish blue versus green. Okay, good. Let's continue. And in this classically BPS sector, there is a Hamiltonian that we can define. So because D0 is just that linear combination of, if we are at classically BPS sector, then we have this equation. So this linear combination of charges equals to D0. So we can write this. So D minus D0, that equals, that originally we call it delta, but now if we want to interpret it as Hamiltonian, then we can also call it H. And that is the 2 times the anti-commutator of Q and Q dagger. So So the classically BPS sector has a Hamiltonian and can be regarded as a supersymmetric quantum mechanics. And so now if we want to study this supersymmetric quantum mechanics, of course, we would like to go away from G Young Mills equals 0. And then we need to understand how G Young Mills correct this Hamiltonian. And there is a non-renormalization conjecture. I will tell you more detail later, but now let me just state this conjecture. That is, the supercharged Q does not receive any perturbative or non-perturbative correction. And but on the other hand, we know that the Hamiltonian will receive correction coming from the correction of the dilatation operator. And let me explain how this correction arrived. So if we assume this conjecture, then the only G Young Mills correction to the Hamiltonian should be coming from the Hermitian conjugate Derger. And this Derger is defined in the radial quantization. And the way we define it is, so to define the Hermitian conjugate, we need to first define the inner product. And in the radial quantization, the inner product is defined from the 2-point function of the CFT. And of course, we know that 2-point function will receive G Young Mills correction. So as the Hermitian conjugate. And then this G Young Mills correction would through the Hermitian conjugate give you the correction of the Q dagger, and then give you a correction of the one loop Hamiltonian edge. And if we focus on the one loop Hamiltonian edge, they will give you the geometry correction coming into the Hamiltonian edge. If we focus on just one loop, then the dagger. So now it might not be clear to you, but at this order, the dagger can be just taken to be the one in the free theory. But I think I will explain this a bit more in later part. Okay. But I mean, if we want to study the BPS operator, of course we would like to not just remain at zero coupling or one loop order, but we can see that now there is a problem, because the dagger will receive in principle all loop correction, and then same thing as the BPS operator. So how do we study the true BPS operator in this framework? And that comes to the Q cohomology. So let me I will show that we can study the BPS operator by considering the cohomology of the supercharged Q. That follows from this standard argument coming from Hodge theory. So in Hodge theory, we study the differential forms, and we also study the Dirac cohomology, and that is the cohomology of the exterior derivative D. And we also know like D squared equals 0. So D defines the cohomology on the space of differential form. That's the Dirac cohomology. And besides D, we also have the codifferential delta. And the differential form that annihilated by both exterior derivative D and codifferential delta are called harmonic forms. And by the Hodge theory, we know that there is an isomorphism between the space of harmonic forms and the Dirac cohomology classes. And now we can make this analogy. So the exterior derivative D in our case is the supercharged Q, and the codifferential delta in our case is Q dagger. So and the 116 BPS operators are the operators that are annihilated by both Q and Q dagger. So they are the analogy of harmonic forms. And then by this comparison, we know that there is a one-to-one correspondence between 116 BPS operators and the Q cohomology class. And this gives us the very important advantage, that is to define the Q cohomology, we actually do not need Q dagger. we only need the information Q, then we can define the Q homology. So the first part of my talk will be the study of the Q cohomology, the 116 BPS operator, and we do not need Q dagger.
Okay. This will depend on G arguments. Q cohomology will still depend on G arguments because Q dagger depended on G arguments.
My next slides will exactly explain this point. So, what are the things that depends on G mills and what are not? So first, by this argument, the Q cohomology only depends on Q, so it does not depend on G mills. So a Q cohomology class is a finite dimensional Hilbert space. Finite dimensional Hilbert space V, and this space V is independent of G mills. But the true BPS state is a vector in the space V, and itself would depend on G mills. For example, so here I draw a schematic picture here. The space itself does not depend on G mills, and this blue arrow denotes the true BPS operator. That is the in analogy the harmonic forms, a harmonic form, and it would depend on G mills. And if we, for example, turn G mills up, turn on G mills, and to some, say, finite G mills, then this blue vector would rotate in this space to the red vector, this one. And so the other states are, the other states are Q exact but not Q closed, and the other states are corresponds to non-BPS states in the classically BPS sector. Any questions at this point?
The number of these states, the blue arrows, will that number depend on G mills?
It will not depend on G mills. So in a particular, in a Q cohomology class, there is only one. For a given Q cohomology class, there is only one one exactly BPS operator, and the others are Q exact. So basically, the way we define the Q cohomology is that we have a Q closed, modeled by Q exact, and if we say we take a particular Q closed guy, call it O, is Q closed, but not exact. And then the V is given by, you consider O plus Q acting on some arbitrary stuff. And the statement is that, let's see, this guy is independent of G mill. The space itself is independent of G mills. But now you want to ask, so we know that inside this space there is a there's a true BPS operator, and that guy is given by, it's not necessary O, because O now is just a representative, but there is a special representative in V. So there exists some operator, let's call it O tilde, and such that Q, of course, Q annihilate, Q annihilate O tilde, and Q dagger also annihilate O tilde. Okay. And this O tilde, the definition of O tilde involve Q dagger, so it would depend on G mills.
Is there a particular reason you say it's finite dimensional?
So if you fix the charge, and then if you fix the charge angular momentum, and then it's finite dimensional, because some particular charge angular momentum, there are only finitely many local operators.
Yeah.
Right. That's so maybe I should add that for fixed J left, right, and QI. Yeah. Any more questions? Good. Let me continue. So now, let me be more explicit. Try to really, for example, construct these O and O tilde. So in n equals 4 super Young Mills, what happened? Okay. So in n equals 4 super Young Mills, I know. Okay. So in n equals 4 super Young Mills, all the operators in the perturbation theory are built from multi-trace of fundamental fields. That is because in 4D, there's no non-perturbative operator. And the typical non-perturbative operators are, for example, multiple operators in 3D and instant operators in 5D. But in 4D, we don't have them. And so we can build the operators in perturbation theory just by taking plating composites of fundamental fields and then try to make gauge invariant combination. And we would call the fields and derivatives by letters, and then the gauge invariant combination of the letters, we will call them word. And now we are interested in classically BPS sector, and they are given so the operators in the classically BPS sector are called the BPS words. They are composed of BPS letters. So here I list all the letters in n equals 4 super Young Mills. We have 6 scalars and 8 fermions, psi and psi bar, and also a gauge field, and also covariant derivative. And now we would like to restrict to the classically BPS sector. So basically, we impose a delta 0 equals 0 condition. That is the, so we call that this is D0 minus 2J left minus Q1 minus Q2 minus Q3. So we require the letter to be classically BPS. So that would, with this, we can get rid of a bunch of non-classically BPS letters. The only field remained are 3 scalar. So this I run from 1, 2, 3. And 3 fermions, and here psi, and also another 2 fermions, lambda, and the field strength. And I mean, this is the self-dual field strength with plus component, and also a 2 covariant derivative. That is this one. So we call that this alpha dot can take plus minus value. Okay. And so these BPS letters can be very nicely ensembled into a BPS superfield. And this BPS superfield has auxiliary variables z plus, z minus, and they are bosonic, and the 3 Grassmann auxiliary variable theta 1, theta 2, theta 3. Oh, so 2 bosonic and 3 fermionic auxiliary variables. And the way we assemble these BPS letters is that we first construct the alpha index with, contract the alpha index from the exterior derivative or this lambda with the z variable. So basically, z variable will take care of how many covariant derivative we have, and then we contract all the I index with the theta variable, and this because they are Grassmannian, the Grassmann variable. So we only have this finite expansion, and you can see that all the component fields, all these BPS letters nicely fit into the component fields of this superfield. Okay. And now, so as I said, we want to consider gauge invariant combination of these BPS letters. And in particular, we will use traces, consider multi-trace expression of these BPS letters. And then we have basically two ways of write this gauge invariant combination. And if we use the BPS letter themselves, and then we have, for example, this expression, we can also write them as the BPS superfield. So taking this z and theta derivatives would actually pick up some components in this expansion. And finally, we would take both z and theta equals 0. And from this expression, there's one thing to notice, that is, if we take the BPS superfield and set z equals theta equals 0, then that is 0. Because we see that every component, every these BPS letters always comes with at least one z or one theta. And this condition will be important later on when we try to write down some BPS words, some cohomology classes. And with this BPS superfield,
Sorry, can I ask a really remedial question, if you don't mind? So from the words, from the letters, which are, each letter is in the adjoint of SUN, right? If I understand.
Right.
And you can just choose to arbitrarily contract some of the letters into a word. I mean, take a trace as you're showing. And so you can get many different, in that sense, words out of the same set of letters, right? Am I right in this?
Right. Yes,
okay.
Of course.
Thank you.
Right. And let me comment on this one more thing. So of course, you can just by taking traces and multiply these matrices and take traces to get gauge invariant combination. But these kind of expressions are highly redundant. There are lots of trace relations. So different trace expressions are related by this trace relation. And the hard part of this problem is to solve this trace relation. And so we have the space of BPS words, and the Q would give us a differential acting on this space. And it acts on the BPS superfield in a very simple way. So Q acting on psi just give you psi square. And this psi square, of course, means the matrix product. And now let me say some words about the non-renormalization conjecture that I stated before. So the goal is to try to argue that the Q action does not receive any G on Mills correction. So first, in Lagrangian theory, the action of Q on fundamental fields is undeformed perturbatively if we have a suitable SUSY preserving regularization. For example, the commonly used regularization is Siegel's DRED regularization. And if we have a SUSY preserving regularization, and then we know that this formula would not receive any G on Mills correction. But this is not enough.
Again, I'm very sorry to interrupt you, but just to make sure, the version of dimensional reduction I've used is where you keep the number of components of fermions, what they would be in 4D, but you regulate all loop integrals using, say, 4 minus epsilon prescription. Is that the Siegel prescription? Just once, yes, to understand?
Yes.
Okay, thank you. Thank you.
So let me take this chance to explain a bit more about this. So, I mean, from its prescription, it seems that there might be some mathematical inconsistency involved, because you keep the so basically you keep the spinor representation at integer dimension, but you consider momentum to be non-integer dimension. But as far as I know, people haven't really encountered any mathematical inconsistency in real computation. Yeah. And there are actually some other more involved SUSY preserving regulator in the literature, but those regulators are less practically useful because they usually are more complicated and not easy to work with. And so actually, whether there is a mathematical consistent whether there is a mathematically consistent SUSY preserving regulator is still not for the I won't say is this question is not close so far.
Thank you.
But of course we assume there exists a SUSY preserving regulator, and then by this regulator we know that this formula will not receive Young-Mills correction.
Sorry, why is Q1 psi something non-zero? This is the correction which you get from 1 to.
Sorry.
Q, I is just made of BPS letters, right?
Yes.
So why is it non-zero? Q acting on psi.
So psi has delta 0 equals 0, but Q acting on it does not need to be 0. Yeah.
So this has some non-zero coupling correct.
Yeah. So in more precisely, there is a Young-Mills.
Yeah.
Yeah.
Okay.
In front. That's from interaction. But you can actually okay. Let me take this opportunity to explain one thing I did not explain previously. So here, we usually write. Let me define psi tilde to be G. Let me see, Young-Mills psi, and then with this, so this should be opposite. With this, we have Q psi tilde equals G Young-Mills psi tilde square. Okay, and then so you can also argue that Q dagger. So now if we consider, let's call it Q dagger 0. So this dagger 0 is the free theory dagger, and then we know that this will also go like G Young-Mills because we use a free theory dagger that will not introduce G Young-Mills, and then by this we know that Q dagger would proportional to at least G Young-Mills square and plus some higher thing. So that's why if we use a free theory dagger, and then the Hamiltonian we have is the one loop Hamiltonian that is proportional to G Young-Mills square. Okay.
Isn't the understanding that if you have a interacting string field theory, then you do have Q psi equals psi square? Isn't that the correct understanding?
I'm not sure. So my consideration here is just purely on the CFT side. Yeah, I'm not sure how to interpret this in the box side.
I mean, in the case of the interacting theory, you don't have Q psi equals 0, right? So only in the free theory do you have Q psi.
Yeah, you can say in that way, right?
Yeah.
In that, sorry. I misheard. So yeah, you mean interacting theory? I thought you said interacting string theory. Okay. So, right. In interacting theory, you have Q psi equals psi square. Right. So, but this is not enough. Like the reason is that we want to act Q not just on single letter, but on some composite of letters. So if we act on composites, and then the way we act it is to use the Leibniz rule. For example, Q acting on AB equals Q acting on A times B, and then A times Q acting on B, and with some potential minus sign depends on whether A is bosonic or fermionic. But the quantum effect may violate the Leibniz rule. But so because of this, we do not have a proof of the non-renormalization conjecture, but we can see that what are the examples of the quantum effect that violate the Leibniz rule. as far as I know, the only known example of such effect is the conical anomaly, but in Engels force Young-Mills, there is no conical anomaly, so we believe that the Leibniz rule of O actually holds in Engels force Young-Mills. And there are more discussion on this point in this paper, but I will not go into detail of the discussion. And so in the following of the talk, I will just assume the non-renormalization on conjecture. Okay, now let me show you the way that how we compute the Q cohomology, and I would show you this particular example. And let me actually just write it. Okay. So we would like to focus on a particular example that has the number of z derivative plus minus 5. Sorry. And we focus on particular charge sector. I. We fix it to be 0, 0, 1, 1, 1. So so this expression this expression does not have any z derivative, and it has 1 theta 1 and 1 theta 2 and 1 theta 3 derivatives. And at this sector, the chain complex is very simple. And the subscript here means the number of psi. So first, we cannot have just a single psi. That is because let's consider SUN theory. The trace of a single psi equals 0. So it starts with V2, the space with two psis, and we can at most have psi cube. That is because we also know that psi z equals 0 equals theta is 0. So every psi must come with a derivative. So at most we have V3. And now let me write down a basis for V2. So V2 has a basis trace. Partial 1, sorry. Partial 1, partial 2 psi. Let me write this partial I, just partial theta I, and partial 3 psi. So this is one basis vector, and there's another one, partial 2, partial 3 psi, partial 1 psi, and also trace partial 1, partial 2 psi, partial 3 psi. Okay. Hey, wait, sorry. I wrote it wrong. 32. Okay. And V3, I can also choose a basis. That is partial 1 psi, partial 2 psi, partial 3 psi. And I have this. So first I can actually anti-symmetrize these three indices. And then the other expression is by symmetrize the three indexes. Okay. And let me call this one O anti-symmetrized and this O symmetrized. So now let's see. Now let me for computing the cohomology, let me first do some small computation here. So Q acting on trace of partial I psi, partial J psi equals 0. That is because Q acting on psi becomes psi square, and for example, we have I psi square partial J psi plus some other thing. But now we have Q, psi squared, but there's only one derivative. So then we will have something that we have some psi without any derivative. And then by our condition here, and this is 0. And by knowing this, and also we also know that Q anti-commute with partial I. I mean, that is just obvious because Q acting on psi just becomes psi squared, and it obviously anti-commute with partial I. And knowing this too, we know that in V2 we have the Q closed guys. For example, partial 1. Trace partial 2 psi, partial 3 psi. So this is one Q closed guy, partial 2 trace, partial 1 psi, partial 3 psi. And this is another one. And there are two Q closed guy. And there is one that is not Q closed. Is this one. Let me see. Partial 1 psi and partial 2, partial 3 psi. So this guy, let me see if I probably need to add one more page. So this guy, if we compute it, so that equals so first the Q cannot act on the first side because the first side only has one derivative acting on it. So the Q must act on the second side. So we have trace partial 1 psi, partial 2, partial 3 psi square. And then expand it, we get this partial 1 psi, partial 2 psi, partial 3 psi. And that's the -2 OA. Okay. So with this knowledge, we know that and also we also know that OS is not inside the image of this of this arrow. So we can write a matrix expression for Q. That's 0, 0, 0, 0, 0, 1. That maps the 3-dimensional space V2 to a 2-dimensional space V3. And this one basically map this operator in V2 to OA in V3. Okay. With this,
So,
you have any questions?
sorry, I forgot. I forgot why I didn't need to keep track of the derivatives in Z. You only had the theta derivatives, right?
Right. I only have theta derivative.
So what happened to the derivatives in Z? You had.
Oh, it's by my assumption. I do not have Z derivative.
Okay.
Yeah, I focus on particular charge sector. That means so basically the number of Z and number of theta derivative can be mapped to this Q1, Q2, Q3 charge, and also the J left and J right. So if we fix the angular momentum and charge, we will fix the number of derivatives. So in this particular case, I have just 1 theta 1, 1 theta 2, and 1 theta 3 derivatives.
I see. So this is some choice of the angular momentum and charges.
Right. Yes. Okay. And now let me let's see. So let me actually also compute the action of Q dagger on this. Okay. Of course, here I've done with computing the cohomology in this particular case. so I mean, basically in this case, we know that there are two cohomology classes for I mean for the case with two two sides, and there is one cohomology class and in the space of three sides. But now let's consider Q dagger. So basically, you can write.
Sorry,
Q...
one more question. How do you see that OS is not in the image of this V2 to V3 map?
Oh, OS. That is because now in V2, V2 is three-dimensional, spanned by these three vectors, and now I can change the basis, so such that V2 is spanned by this one, that one, and they are closed, and also this guy. This guy is not Q closed, and this guy mapped V3 becomes a Q exact guy. So nothing mapped to OS. And in other words, the OS will be a representative of the Q cohomology. So the representative are OS in V3 and also these two Q close guy in V2.
Okay.
I have a nice question. Like
yes.
when you act by the derivative on the psi and you act from Q on the outside, just a single derivative, right? So it will give you d of psi square. Now, d of psi square would be psi d psi plus another psi d psi, right? So why would that vanish?
Sorry, which one? Which expression you are?
I mean, when you're acting with Q on the trace of d1 psi, d2, d3 psi.
This or this one?
Yeah.
Or this one? For example?
I can't see your cursor. Yeah. Even in that one. So when you get trace of di psi square, why do you say that is 0?
Yeah, let's see. So this guy is 0. That is because if you try to expand it, so we have psi square here, but there's only one derivative.
Yeah, true.
And so there will be so after you act so this partial I on size, there will be a side without any derivative. And so after we done all these computations, we would like to take z equals 0 and theta equals 0 to recover the components.
No, my question is whether you're assuming that di acting on psi square would vanish because psi is a Grassmann number or something. Is that the assumption?
Oh no, I do not assume that, because psi is also a matrix. So psi square is non-zero.
Psi square is non-zero.
Yes,
fine.
because psi is a matrix.
So then why is di psi square dj psi 0?
Yeah, so the reason is that I use this condition. So I mean so in the end of the day, I would set all z and theta equals 0.
I see.
That is because I want to recover. I want to recover these kind of formulas.
I see. Okay.
So in the end of the day, I would set z and theta equals 0. So if there is a psi without any derivative, then it would be 0.
I see.
Okay. Good. Now let me continue. So you let's see, use black. So Q can also be written as psi square partial psi, at least formally. And I will not tell you how I got this, but roughly Q dagger will be proportional to trace of. It's just very naive way of computing a dagger. You basically replace a derivative with, we replace psi with psi derivative and psi derivative with psi. So you get this formula. And then with this, you can also, let me do this computation. Compute Q dagger, for example, on OS. And that's proportional to trace psi partial psi square and acting on trace partial 1 psi partial 2 psi partial 3 psi. And so here the way we do it is basically we need to pick a pair of psi and then replace it by a single psi. That's how this action works. And so I mean because I symmetrize all these 1, 2, 3 indices, so it doesn't really matter of which two psi I pick. You will get this expression. I just write it proportional. I do not keep track of the overall numbers. You get this, and this is 0. That is because the theta derivative are Grassmann, and now I symmetrize the theta derivative, so I get 0. And you can do similar computation, Q dagger on OA, and show that proportional to basically just by the symmetrization replace it to the anti-symmetrization. But then now this is non-zero. Okay, so by this we know Q dagger is, you can also write it as a matrix form 0, 0, 0, 0, 0, 1. And the Hamiltonian, these two Q dagger Q. Let's consider Hamiltonian on V, let's see, V3. So because let's see, sorry. Sorry. On let's see, on V2. Right. And then you have 0, 0, 1, 0, sorry, 0, 0, 0, 0, 1, and 0, 0, 0, 0, 0, 1, and that give you 0, 0. Wait, oh, is it? Let's see.
That is before the matrix.
Yeah, it should be on V3, I guess. Yeah, okay. Anyway,
so Q dagger acting on something must be non-zero because there is a 1 in the matrix. So which is it?
Q dagger on something.
On OA, I see. On OA, it acts to be non-zero, is it?
Yeah.
Okay.
Right. On OA is non-zero. Yeah. Okay. So basically, in this case, I mean, I get this Hamiltonian and it's already a diagonal. So we have, so basically on V3 there is a BPS operator and there is a non-BPS operator. And also if we keep track of the coefficient, we also we have also computed the anomalous dimension of that BPS operator, and sorry, of that non-BPS operator. And that particular non-BPS operator is actually the Conicia operator. Okay. Good. So I've shown you at least roughly how we do the computation in this very simple example. So now let me tell you. By the way, I mean, as far as I know, there's no time limit for TIFR seminars. I hope my assumption is correct. Okay, good. So now let's continue.
I have another question.
Sure.
Like the Hamiltonian acting on which operator is it non-zero?
Let me see. I may, so for these matrices, I may write them a bit wrong. So I mean, there might be there. Sorry, I should write transpose. There might be transpose on this, I think, and then this one is this. And the Hamiltonian, so this Hamiltonian is 2 by 2, and V3 is 2-dimensional.
Yeah.
And yeah. So and also let's see, V3 is annihilated by Q, but does not annihilate by Q dagger. So here I
So
drop
V3
Q
is the
dagger.
object on which the Hamiltonian acts to give that matrix. Is that
Right. V3 is a space
I see.
that Hamiltonian act.
And which operator in V3 is the operator?
So yeah, right. So V3, I pick these two. I can consider these two bases, and let's see. So OS. Right. So we see that OS is annihilated by both Q and Q dagger. So here I show that is annihilated by Q dagger.
Yeah.
Yeah, and also you can also see that it should also be annihilated by Q because I mean it's just quite trivial because you have too many sides than the derivative. So OS is the true BPS operator.
Now, if V3 is operated by both Q and Q dagger, then
No. But OA only annihilated by Q, but not Q dagger. So OA acting on Q dagger, Q dagger acting on OA is non-zero.
I see.
Right. So that's why I get a BPS operator and a non-BPS operator. Any more questions?
So Chi-Ming, the one that has this non-zero eigenvalue under the one loop Hamiltonian, at strong coupling, how does one know whether it'll end up being a string state or a black hole state?
That's a good question. So could you wait a bit, and later on I will discuss the interpretation of them.
Yeah.
Okay. Good. Okay. Now.
The Q dagger that you this Q dagger is it just one loop or the full non-perturbating?
This is only one loop. So to be more precise, there's a G on Mills in front of it.
Yeah. So Q dagger on OS equal to 0. This is just a one loop statement. It can OS can become non-BPS at higher loops.
Let's see. Right. Yeah, you can say that it's just a one loop BPS. Yeah.
Sorry, but don't you have a non-normalization theorem?
Oh, but I mean, for Q you have a non. But the question she is asking is this computation.
Okay.
So this computation tell you that OS is not only the representative of a Q cohomology, but it is also the BPS operator, but it's only one loop BPS. Yeah. Good. Any more questions? Okay, very good. So now, of course, from this computation, you can see that this is a very hard problem if you want to go to high charge and large N. So here, because I mean, the charge is small, and we also do not have many sides, we can write everything as a single trace. But if you consider large charge, and there will be lots of many sides, and then you have single trace and multi-trace expressions, and there will also be trace relation among them. The problem will quickly becomes very complicated. Okay. Good. And so now let's come to the next part. I will show you what we call the graviton operators, black hole operators, and this near-SUSY spectrum. So first, even though I said the problem is hard, but the problem if we restrict to single trace operators, this problem has already, the Q cohomology has already been solved. So the idea is that first, Q does not change the number of trace. So we can fix the number of trace. Basically just ignore the trace relation and focus just on single trace operator. And we can define the Q cohomology on the space of single trace words. And on this space, the single trace cohomology class are represented by the operator O-grav, and I will call them graviton operator, but I will explain why we call them graviton operator later. But let me just first explain their properties. So first, these operators are given by this formula. So as I said, they are single trace, and the particular thing about this operator is that inside the trace, every psi only has one derivative acting on it. So now let's first ignore the derivative outside and just look at this trace form. And by this property, this guy is obviously Q close. It will be annihilated by Q, because every psi only counts in one derivative. And if we add Q on it, we will get Q squared. And as I explained before, if we have a single psi acting on Q squared, that will give us 0, because in the end of the day, we need to set the O0 variable to 0, and then if you have a psi without any derivative, it will be 0. And now we also know that Q commutes with all the derivatives. So we can add derivative outside the trace. It will not change the fact that this operator is annihilated by Q. So we have this. And also the thing inside the trace are symmetrized. That is because the commutator of psi will be Q exact. That's just, I mean we know that Q psi equals to psi squared, and this can also be written as psi anti-commutator. And if you add derivative on psi, because we have theta derivative, theta is Grassmann, so that can change psi to be anti-commutator. We can change the anti-commutator to commutator. So this, yeah, I should probably be more precise. So the thing inside are symmetrized or anti-symmetrized, depending on whether, for example, this guy is fermionic, and this is bosonic. So the thing inside are symmetrized or anti-symmetrized, depending on whether and the derivative of psi are bosonic or fermionic, and that's because the commutator of any commutator of them are Q exact. Okay. So the claim is that this formula gives us all the representative for the single trace Q cohomology. I will not show you, but it's actually not hard to see that for single trace you do not have any other new cohomology other than these guys. And furthermore, you can also consider a Q dagger acting on the graviton operator. And it's also quite easy to see that the graviton operator are one loop BPS. And I also expect that these are actually BPS beyond one loop. But so far, the result we have is just that the one loop Q dagger annihilates all graviton. But this part, and if we just want to consider Q cohomology, this part is not that important. The important thing is.
Sorry, perhaps a silly question, but in your O-grav, once I act Q on it, it's true that it becomes psi squared, but there is also these derivatives outside, right? Why don't they act on the new psi? Like the derivatives inside, there's only one derivative per psi, but there's also these outside derivatives.
Yes, you are right. Let me try to see what happened. Let's see. Yes, you're right. Let me recall what. Let me see. Yes. I think it would be harder to see like whether it's Q closed. Let me see. So I think, yeah, but this is true, like it's Q closed. Let me see. How do we see this?
I think if Q and Q dagger are both 0 acting on Go graph, then you would have the Hamiltonian itself to be 0. That can't be, right?
No, so that's true. For one loop, it's the Hamiltonian acting on the graviton operator. One loop is 0.
But then what about his question? I mean,
let me see. Yeah, I forgot the argument, but it's true that these are Q exact. But yeah, but my argument, the argument I just gave, that does not involve the extra derivative. But even if you have extra derivative, you can still argue that it is annulled by Q. But I forgot a quick argument of this statement. Okay.
Okay, thanks.
Okay, good. We can continue. So let's see. Yeah. And now let me try to explain like why we call them graviton operator. And in the larger limit, we can in the larger limit we can count how many single trace cohomology we have, and then basically we can compute the partition function for the single trace cohomology, and then we can match this partition function with the single graviton partition function in the bulk, and in that case we find the exact match. So that's why we call these graviton operator, graviton operator.
but in order for to define a partition function, wouldn't you need a Hamiltonian that's non-zero?
Oh, the partition function, I mean that you grade it by the angular momentum and R charges. You only grade it by chemical potentials, and of course the Hamiltonian is 0, so the fugacity associated with the Hamiltonian.
So it's more like an index.
Yeah, you can say that. Good. And now to get the multi-gravitons, we just need to simply consider products of the single trace cohomology, and of course modular trace relation. And we will call these kind of cohomologies graviton cohomologies. And of course, if you consider products of cohomology, that will give you new cohomology, modular trace relation. So some products can give you something trivial, but some other products of, two Q close, the product of two Q close things cannot sorry, let me say again. If you consider product of two Q close things, it will always be Q close, and it can be Q exact, but it cannot be non-Q closed. So you consider products of cohomology that will give you some cohomology, and it can give you trivial cohomology due to trace relation. Okay. So now we have a very natural interpretation that is the graviton cohomologies corresponds to all the graviton states, including single graviton and multi-gravitons. And this statement is at large end, but importantly, we see that our definition of graviton cohomology actually makes sense at finite n. So we can kind of extend the definition of graviton from infinite n to finite n. And in that sense, we can distinguish graviton versus non-graviton at finite n. and the thing that inside this non-graviton may be black hole. So that's our way to distinguish graviton versus black hole at finite n. Any questions at this point?
Yeah, can you elaborate on your extension finite n?
Okay, so first, by our argument here, an infinite n, the single trace cohomology matches with the single graviton state, and multi-trace cohomology. I mean, sorry, it's not. You shouldn't say multi-trace cohomology. Just products of single trace cohomology. That's what we call graviton cohomologies. Matches with an infinite n's multi-graviton states, and now by our definition of graviton cohomology, that actually makes sense at finite n, because first the single trace cohomology makes sense at finite n. We just forget about trace relation and always work with single trace, and the graviton cohomology are just product of single trace cohomology, so that also makes sense at finite n. So with this, we have an extension of what do we mean by graviton at finite n, and then we can talk about whether a cohomology class is a graviton cohomology or not. That's our way to distinguish a graviton versus something potentially being black holes at finite n.
So at finite n, there would be a there would strictly be reduction in states, right? Because of trace relations.
You mean stringy states? Or?
So there would be reduction. There would be reduction in number of states, right? Because of trace relations at finite n compared to infinite n.
So I do not quite get you.
No, I just mean that at finite n there will be a reduction in number of states compared to infinite n. Because
yes, right. Yeah, there might be reduction. Yes, and infinite n you can forget about trace relation, and finite n you impose trace relation, then you will get less graviton cohomology than you have at infinite n.
Okay.
Yeah.
I have a question. Like when you have a single graviton, according to the usual ADS-CFT, I mean the corresponding state in the n equals 4 Yang-Mills is just trace f square, right? F trace f. Is there any way to see that here?
Trace of what?
Trace of f mu nu f nu sigma, for instance, would be g mu sigma.
Oh, I know. So here, when I say graviton, they are actually 10D graviton. So they are graviton in ADS5 times S5. So if you think of in the ADS5 sense, what I call graviton includes all the KK towers.
Yeah, but the single graviton, for instance, the 0th component of the KK tower would correspond to the basic trace FF sort of operator in the Yang-Mills side. I mean,
sorry, I think that this is not quite relevant to this talk. Maybe maybe we should let Chi-Ming proceed, because already yeah, please.
Okay. Good. So now after introducing the graviton operators, we can look for something that are not graviton cohomology. Okay. So first, we actually already know that the graviton the graviton are not enough to capture. To give you the enough states for black holes. So if we want to focus on the black hole region, we need to have angular momentum and charges are all of order n squared. And so in this case, if you can count how many graviton operators you have, then that's roughly e to the n to the 5/3, and that's much smaller than e to the n squared. So graviton cannot account for the black hole entropy. So we must have non-graviton operators. And in other words, actually, a typical microstate should actually correspond to non-graviton, because e to the n squared is much larger than e to the n to the 5/3. So typical black hole microstates are non-graviton. And because of this, we will actually refer non-graviton operators as black hole operators. And as I have already emphasized, that this computation is very hard because of the trace relation. And the thing we do is actually do some brute force enumeration of all the BPS words up to some large classical dimension, and also explicitly enumerate all the trace relations. So basically, the way we do is to use component forms of these matrices, and then in that way, if we plug the components forms, and then the trace relation will be automatically solved. And by using this method, we actually construct a million-dimensional classically BPS Hilbert space. And then we have the Q acting on this Hilbert space. And then by using that, we constructed roughly 10 to the 5 Q cohomology classes. And then we also do similar thing for Q dagger. We compute the one loop Q dagger and also one loop Hamiltonian, and also diagonalize the one loop Hamiltonian on this Hilbert space. And roughly, so this one loop Hamiltonian will actually be block diagonals, because we can separate the space in the subspace of different charges. So roughly, we have the 10 to the 4 dimensional blocks of the one loop Hamiltonian. And then diagonalizing this one loop Hamiltonian, we compute the one loop anomalous dimensions for roughly 10 to the 6 operators. Okay. So we mainly focusing on this for SU2. And we can grade the charges by consider a different value of this particular combination, 2 times D plus J left. So this combination, we call it level. So at level 24, so I mean, we basically go up to level 24. And we've basically found that almost all the cohomologies are graviton cohomologies, except this particular, except one cohomology class with these particular charges, and it's level 24 and has dimension 19 divided by 2, and also angular momentum 5 and R charges 3 half, and this formula consists of 7 psi. And you can see that the dimension is actually much larger than n squared. But these angular momentum and charges are roughly of order n squared. And this is kind of expected, because we know that the black hole will show up roughly when the charges are of order n squared. And we also try SU3 and SU4 up to some level, but for all these cases, we do not find any non-trivial, we do not find any non-graviton cohomology.
Chi-Ming, what is your conclusion from the exercise on the above slide?
Sorry, say again?
From the diagonalization of this giant Hamiltonian, what do you conclude?
Oh, so the result here only concerned about this part, and I will tell you something about the one loop Hamiltonian and the one loop anomalous dimension in some later part.
Okay.
Okay, good. So after our paper, there are a couple of papers from Korean group, and they in particular they found out an explicit and concise expression for the cohomology we found that take this form, basically this form. And you can actually, you can see that it's a triple trace. And so for example, the first one, you can see that it's a graviton operator, because each psi inside the trace has only one derivative. And second guy is also a graviton operator. And the third one is not Q closed. Otherwise, it will be graviton cohomology. And in particular, this one will have, this one by itself will have non-zero anomalous dimension. And you can actually interpret it as a massive single string in weak coupling. But of course, as we argue that, so I mean, as we argue that the cohomology will be independent of G mules. So at weak coupling, you can interpret this as some bound states of two graviton and one string, but at strong coupling, you can interpret that as black holes. So this is just a representative, but we can actually obtain the one loop BPS operator, and by consider some linear combination of this operator O with some Q exact operator, such that this linear combination will also be annihilated by the one loop Q dagger. And it's the one loop BPS operator is this linear combination, and all these O3 up to O17, they are Q exact operators. And this linear combination is also annihilated by Q dagger. So these are just give you some formula for what are these O prime, and Q acting on these O prime give you the O here. Okay. And let me comment on another interesting thing. So let's see. Okay, good. So I mean, of course, the thing here, we need the information of Q dagger, and that's equivalent to the knowledge of the one loop Hamiltonian. And you can actually consider the one loop Hamiltonian at generic and even non-integer n formally. And so from this analysis, there's very interesting structure appear. That is, the multi-graviton operator are actually a BPS for all n. I mean, I actually one loop BPS for all n, while the black hole operators are actually kind of accidentally BPS only at some special value of n. In particular, we can study that particular cohomology class at level 24 and compute the one loop anomalous dimension. And so it's from the work from the parameters group, and they found out this plot. So these red lines denote the anomalous dimension of that particular non-graviton cohomology, and it has zero anomalous dimension at exactly n equals 2, but it will have a non-zero anomalous dimension if you go to large n, if you try to extrapolate to large n. So with this, we can have a quite interesting interpretation. And at large n, you can interpret these three as some weakly bound particles. So at large n, you can interpret this operator as some bound states of two graviton and one string. And if you decrease if you decrease n in the bulk, that corresponds to you go to a bulk strong coupling, and then the interpretation will be like a bulk strong coupling, that bound state of two graviton and one string will become the black hole. And of course, this is just some qualitative interpretation, and that we can try to draw from this analysis. I mean, this computation. Okay.
Sorry, I mean, the fact that it has some anomalous dimension at higher n, why does it make it a non-black hole state? It could just be a black hole state which is very heavy, right? Not necessarily supersymmetric.
Oh, so you can consider, say, infinite n. And infinite n, the bulk becomes weakly coupled, and infinite n, relatively, these are actually also light. So these are, I mean, this triple trace is heavy at n equals 2 because it is comparable. The dimension is larger than n squared. So you can interpret that as some black hole microstates because its energy is greater than n squared. But at large n, and these are actually light. So
these are light at weak coupling, right? At weak coupling. I mean, what happens with strong coupling? Do we know? How do
So you mean bulk strong and weak coupling, or boundary strong and weak coupling?
Boundary strong coupling.
Oh, let's see. So, okay, so let's focus on angles 2 and try to go from boundary weak coupling to boundary strong coupling. As we just argued that the Q cohomology itself will not be affected by the G-Young mills. So inside that finite dimensional Hilbert space, there will be one BPS operator that corresponds to some BPS black hole microstate at angles 2. Yeah. So, and that would still, I mean, roughly given by this kind of triple trace. And now we try to go in a different direction. Try to go from small n to larger n. That's in the bulk weak to in the bulk strong to weak coupling. So the plot here is for n, and we see that if we go in the bulk from strong to weak coupling, of course these operators are, I mean, so at small n they are heavy, but at larger n they are actually relatively light. So there should be some perturbative bulk excitations at large n. And then in that case, there's a straightforward interpretation as some bound state of 2 graviton and 1 string.
Sorry, I mean, just let's take n equal to 4 or something, n equal to 5. Then in that case, this operator, is it BPS? It's not BPS, right? It has
It's not BPS.
So
I think
once it is not BPS, then as you increase lambda, its dimension just go very high also, right? At very strong at a very strong coupling, at very high lambda.
So okay, the dimension will still not be infinity if you turn on lambda to lambda.
My question is, how does one know anything about that?
Oh, it's hard to know actually. Yeah. But you can actually go to this picture. Yeah, from this picture. So first they are in class. I mean, they are non-BPS, but they are still classically BPS. So if we tune Young-Mills coupling from weak to strong, the classically BPS guys are still light in some sense because they are still at the bottom of the spectrum.
Some of these red lines can go off to infinity or not.
You can find a path, go to infinity, that no level crossing occur. And in that case, all these red lines are still at the bottom of the spectrum.
Okay.
Yeah.
Okay, thank you.
They will not go to infinity. Okay. They could go to infinity in the case that all these blue and green should also go to infinity. But yeah. They're still light this guy.
I have another question. Like when you're considering issue 2, that means that n is very small, and that means that the loop corrections in the string theory would be quite large.
Yes.
Right?
Yes. Right.
So how is that handled here? I mean, how is that taken into care?
Oh, here I just focus on the CFD side, and then try to make some I try to give some bulk interpretation. Yeah, I did not do any bulk computation, and you are right that for SU2 the bulk is strongly coupled, and in that case, the interpretation of this guy will be some highly quantum and small black hole.
I see.
Okay, good. Yes. Okay. Of course, the thing we found is just a single non-graviton cohomology, and you may ask that. I mean, of course, we know that there should be many more non-graviton cohomology, and in this paper from Korean group, they figure out a very nice way to find non-graviton cohomology at higher level, higher angular momentum, R charge, and also the classical dimension. And you can consider the space of BPS words constructed out of diagonal psi. And in that case, if you work with diagonal psi, then the Q acting on this space is trivial, Q equals 0, because the Q acting on psi gives you psi square. Psi square actually means anti-commutator of psi. And if you have diagonal psi, then the anti-commutator vanish. And you can actually further argue that the graviton cohomology is isomorphic to the space of this V diagonal. And then by comparing the dimension of this space with the superconformal index, we know that if there are some mismatch, we know where the non-gravitons should appear. And then after we know the charges of these non-gravitons, then it will be not hard, or at least not relatively easy to explicitly construct the non-graviton cohomology. And in particular, they focus on the BMN sector, the sector with only theta derivatives. And they found an infinite family of non-graviton cohomologies at level 24, 36, 48, and so on. Okay. So the final part of my talk, I would tell you something about non-BPS operators. So first, let me show you the result of the exact diagonalization of the one-root Hamiltonian for SU2 and SU infinity.
This non-graviton cohomologies, this non-graviton states, they are for all n, or is it some particular n?
Oh, they are SU2. Sorry, also SU2. Yeah. So far, there is no SU3 and higher non-graviton cohomology has been found.
Okay.
That one is a very important thing that we are trying to do in the future. And okay, good. So here, and we can compute a smooth histogram, and the delta is basically the anomalous dimension with some normalization by Letov coupling lambda. And so this plot is so you can think of this law roughly as the density of states, and with some smoothing, because I mean, of course, the density of states is discrete, and so we use some smoothing function to compute law, and this and that one are the spectrum for the SU2 and SU infinity case. And a very interesting feature for if you try to compare the SU2 and SU infinity case is that for SU2 there is something looks like a gap in the spectrum, but for SU infinity there's no. It looks like there's no gap. But of course, because the spectrum is discrete, there's always a gap. But just after some smoothing, this feature appear as, I mean, it looks like SU2 has a gap after smoothing, and SU infinity has no gap after the smoothing of the spectrum.
Actually,
and then
one can look at the lowest line non-zero eigenvalue, and then you may be able to see the gap.
Yeah, there's an absolute gap, right?
So there is an absolute gap for SU2.
Let me see. I have some. I need to find out the value in my paper. Let me see.
And this calculation can be done for other n's also?
Yes, but other n we have less state, and then in that case the plot will be more bumpy, and in that case we will not think that our data is reliable.
I was wondering what would be the scaling of the gap with n.
Oh yeah, that's the thing. Okay, so far from our data, we couldn't get the scaling of the gap with n, but that would be our goal, because there is some prediction of the scaling of a gap with n in the literature from the bulk computation. Yeah, so okay, let me Of course, this gap depends on, I mean, on the charges. So let me try to write some number. So if you consider SU infinity, you consider charge 2, 0, 2, 2, 2, and roughly the gap is 0.35. And for SU2, if you consider 2, 0, 2, 2, 2, the same sector, and the gap roughly is 1.38. So if you even if you look at the absolute gap, it's I mean, SU infinity is still smaller than the case of SU2. But of course, here is not absolute gap, is the gap after smoothing. So it also depends on how many light states you have. Okay. So in the bulk computation, there's a nice discussion about the gap. That is, we want to consider the near horizon limit of a near supersymmetric black hole. And in that case, the geometry becomes ADS2 times S3 times S5. And if you consider type 2b through graph on this space and do the dimension reduction, you get a 2D n equals 2 JT supergravity. So near the throat of ADS2, of course, for the black hole, we have SU1/1 symmetry. This symmetry is generated by Q and Q dagger and also this delta. And in this near horizon limit, the SU1/1 symmetry is enhanced to SU1,1/1 symmetry. And the n equals 2 Swazian theory, living on the ADS2 boundary, has that's actually given by the Goldstone mode of the spontaneous symmetric breaking from local SU1,1/1 to global SU1,1/1. And this n equals 2 Swazian is actually one loop exact, and you can compute the density of state exactly. So here I draw a schematic picture for the density of states. First, there are a lot of true BPS states at 0 anomalous dimension, and then there's a gap for the non-zero anomalous dimension, these non-BPS operators. And in the bulk, they also they see that the gap is proportional to some number divided by n squared, and this delta tilde star is actually some explicit function of angular momentum and the charges that can be computed from in the bulk side. So the thing we see is that our classically BPS spectrum that's defined at weak coupling, that's just a one loop spectrum, qualitatively agree with the near BPS spectrum at a strong coupling. So qualitatively basically means that this qualitative gap, they both have a gap. So with this qualitative evidence, we try to make this conjecture. That is, the spectrum of classically BPS sector in a larger limit has a gap that depends on lambda, and which is a continuous function of the 12 coupling lambda, and has this weak coupling expansion. So we try to conjecture that even at weak coupling, the gap is also scaled with n squared, and so this numerator has a small lambda expansion, and if we are powerful enough, if we can go to larger n, we should be able to match from our analysis to extract this delta tilde 1, the one loop guy, and at delta equals infinity, it should match with the bulk result, this delta tilde star. Okay, and of course, if we really want to give more evidence of this conjecture, we need to go to larger n and larger charge. Good. So now, and let me conclude my talk by giving some outlook. So first, it's about this conjecture. So as I said, like, if we want to give more evidence for this conjecture, on the CFD side, sorry, could you guys hear me?
Yes. Yes.
Oh, it looks like my iPad just stopped. Okay, let me see. I need to join the Zoom again for my iPad.
We can see your screen.
Wait a second. Yeah, let me see. My iPad stopped. Wait, maybe let me share using my computer. Let me see. Wait. Okay, could you guys see it?
Yes.
Okay, good. So, of course, we can try to go from weak to strong coupling, and by going to higher loops, and that means larger lambda and larger n. And also, there's another way to go from strong to weak coupling, that is to include more stringy and deep band correction. And then the hope is, if we go in from these two directions, we will be able to give more evidence of this conjecture. And another direction is that, of course, right now, the new cohomology I show you, the non-graviton cohomologies, are all SU2 case. And for SU2 and above, so far, there's no non-graviton cohomology has been constructed. So at strings, there's Kim gave a talk, and they try to compare the superconformal index with the graviton cohomology that computed using this computed by diagonalizing the matrices. And then they found out that at level 24 for SU3, there's also there should be a non-graviton cohomology. But right now, so far, still no explicit construction for this cohomology.
You had computed SU3 cohomology set up to some level, right? What was that?
Level 19.
I see.
Smaller than 24. And this result is actually quite surprising, because for SU2, the first non-graviton cohomology is also at level 24. But before their result, we all expect that for SU3, the non-graviton cohomology will appear at higher level. Okay. And so it will be interesting to, so their result basically show that there should be some non-graviton cohomology at this level, and it will be interesting to explicitly construct this cohomology. And with this, maybe it's possible to learn more pattern of the non-graviton cohomology, and hopefully we can write down more non-graviton cohomologies at higher n. And finally, if we consider, say, large n at fixed large charges, say both angular momentum and the R charge be of order n square, but we also allow some errors of these charges. And so say there are some error of the angular momentum and the R charge will be of order 1. And then at each precise angular momentum R charge, there is one root Hamiltonian. But if we allow this error, so there will be some randomness. So that kind of naturally give us some random matrix. But on the box side, we also know that there is a duality between JT gravity and also the random matrix theory with Gaussian unitary ensemble. So this is by famous SSS paper. And this paper, the result has been generalized to angles 1, angles 2, JT supergravity. So one very natural question to ask is that whether there's any relation between the random matrix show up on the boundary and also random matrix show up in the bulk. Okay. So that's basically all the thing I would like to say. Thank you very much.
Okay, thanks, Chi-Ming, for a wonderful talk. We have had many questions, but if there are some pressing questions, maybe Zoom audience can go first.
Yeah, so I have a question. Like you said that the Hamiltonian for this case was 0, right? Because both Q and Q dagger cohomologies were exact. Isn't that correct?
You mean for, let's see, sorry, which case you are talking about? You mean this case?
Yeah. So yeah, I'm talking about the case where you said that the Hamiltonian, since both Q and Q dagger have 0 values acting on the size, the states, the Hamiltonian would be 0. Isn't that correct? So in that case, how do you find a random matrix Hamiltonian?
Oh, wait, no. So okay, you're asking. So
I don't remember the slide which you where you showed that. You can go.
sorry, for BPS operator, right? Both Q and Q dagger should annihilate the operator.
Yeah.
But in the classically BPS sector, there are also non-BPS operator. And so they are classically BPS, but receive anomalous dimension. And the discussion here, I'm focusing on the non-BPS, on this classically BPS sector, and there
So
will be
at
some.
one loop, do they receive corrections?
Yes. So there are some operators in the classically BPS sector, they receive one loop anomalous dimension.
Yes.
Okay, how about here? Any more questions? All right, if there are no further questions, let's thank Chi-Ming again.
Thank you.
Thank you, Chi-Ming.